Hi, everyone. Good morning. How many of you are from quantum computing? Just to assess really quickly. Everyone. OK. So I was told to keep it high level for not quantum computing people, but then I can continue with also the details. So yeah, I'm a quantum libraries engineer at NVIDIA. And today I'm going to talk about how CUDA-QX and AI are coming together to accelerate quantum computing. In particular, I will talk about GPUs and machine learning and how they can help quantum computing in its development process and solving quantum hardware and software challenges. I mean, some basics. So, well, I mean, classical computers rely on transistor, which can implement the bit. We'll keep it really short on this one. The bit can be measured exclusively in 0 and 1, while quantum computers rely on qubits. And the qubit, well, has this property of superposition, where the qubit can be in 0 and 1 at the same time. So we can say, that the qubit is 0 and 1, in a linear superposition. And the qubit can be implemented with several different quantum technologies, like superconducting qubits, trapped ions, neutral atoms, and photonic qubits. Each one of them have pros and cons, but all of them are subject to errors and noise. So qubits, in order to remain stable or their information to be stable, need lots of classical compute resources. And that's why that's why we picture quantum computers to be tightly and seamlessly integrated with AI supercomputers, because we need AI and parallelization to make fast decision making. We need to read out, control our quantum computers, and we picture different technologies to be integrated in the AI supercomputer through, for example, the vendor control system or other control systems directly to NVIDIA AI superchip. And this can help us to, of course, control the quantum computer, but also retrieve the data directly from the quantum computer and feed it into physics models, for example. So this is probably the next step. And once we have integrated quantum computers at scale and we are able to have real-time control, we would use CUDA-Q, our platform language and compiler, to control the AI quantum supercomputer. So this was a little bit of the vision, but why is NVIDIA taking up on this challenge? It's because GPUs and NVIDIA has been at the center of several computing revolutions. In the beginning, it was scientific computing, then it became deep learning, and afterwards, generative AI. And well, quantum computing is going to probably be the next big shift. And well, we want to be able to provide the capabilities, the infrastructure, the algorithms, the hardware, the software, everything that can allow quantum computing to be integrated in real applications. So yeah, NVIDIA is not building qubits, and this is something that I want to highlight, but we are building everything else. So NVIDIA is really trying to integrate tightly the AI supercomputer with quantum computers. Okay. All right. And well, we believe that AI has been a transformative force, and AI infrastructure and AI algorithms are going to be the core of quantum applications development and quantum hardware development. And our team has identified several areas where AI can contribute to the development of quantum computing. I'm going to illustrate just a few of them. Okay, we have a whole review paper about this. Okay, the first one, of course, is AI for better hardware. On the left, you can see some plots. And well, just simply the one above is representing the dephasing, and it's a form of decay of a quantum system. And the other one is relaxation due to the decoherence of quantum technologies or quantum systems. I mean, this is just representative of the fact that qubits on their own are going to die, okay? But what we can do, first of all, is to develop better qubits. And for this reason, we can guide the design process of qubits in order to reduce error rates and extend the coherence time. And well, we can also do this in a larger scale in order to guide the design of the whole device, okay, in order to actually avoid also environmental noise. And yeah, of course, techniques for these are machine learning for Hamiltonian learning. The Hamiltonian is the mathematical formulation of the behavior of a quantum system. And machine learning also for quantum device characterization, for example, qubit tuning, qubit noise characterization, and other properties, and also improving measurements. The next one, once we have better hardware, this is not enough. We also need better quantum circuits. And we have this process called compilation. We want to translate automatically an application to a quantum circuit. And we don't want to do this anymore by hand, because currently this is done by hand, but we want to do this with a compiler, which can actually harness the potential of the hardware and can create quantum circuits that are efficient, noise resilient, faster, and yeah, all the properties that are amenable for quantum systems. So yeah, machine learning and AI, in this case, for example, LLMs and reinforcement learning can help in quantum circuit synthesis. Later I'm going to explain GPT-QE, which is a generative quantum eigensolver. And also it can help in just creating circuits of any type with reinforcement learning, but also in variational quantum circuits or in other parameterized forms of circuits, reinforcement learning can help in generating this right set of parameters. And also there is the possibility of preparing a quantum state, which is usually the first step for several algorithms, also in quantum simulations, which is going to be one of the first killer applications of quantum computing. Yes, so once we have the hardware and the circuits, of course we need to run this. And yeah, the next step is to measure out our results. And the AI can help us in improving the readout of our solutions. Because if we are not able to read out from the quantum computer, then why did we do all this effort? And yeah, machine learning can help us in improving error mitigation and also qubit readout. And convolutional neural networks have proven to be actually a quite useful tool. We had a 56% reduction in error for single qubit and 32% in multi-qubit readouts. And this is really important, really fundamental, because I will show you next, but real-time quantum computing requires real-time, efficient, and high-quality measurements, okay? All right, and well, machine learning for error mitigation during execution times. Well, we have machine learning for reducing the number of resources. So we have 25% of lower computational resources and 50% of lower runtime overhead. Lastly, this is the moment that I wanted to arrive to. It's AI for error correction. For those who don't know what is error correction, this is a clever way of spreading the information of a single physical qubit over multiple physical qubits. And whenever one of these physical qubits are, I don't know, their information is getting ruined because of the environmental noise, then we can gather the information from the group of physical qubits and retrieve the original information. And this is a form of noise resilience, and this is going to be the next step of quantum computing in order to reach fault-tolerant quantum computing. Well, and what are the secret ingredients for error correction is an error correcting code, which is the recipe with which we spread this information over multiple qubits. And decoders. Decoders are these clever algorithms that are able to read out during the execution some error signals and take decisions during real time and provide a possible error correction for the quantum circuit. So yeah, we have examples of AI for code generation and AI for decoders. And later I'm going to explain and illustrate some part of our success with decoders. Well, we have mapped these areas, and we have provided already some solutions. This is only the initial set of solutions. Stay tuned. In the future, we're going to have really cool and interesting news for you. And, well, I want to really quickly summarize areas of quantum computing where AI is going to be really interesting. So first of all is quantum computing for deployments, for quantum error correction, hybrid algorithms and applications, AI for calibration, control, and readout, and AI for quantum computing development, accelerated application development, circuit design, dynamical simulations, noise modeling, and practical post-quantum cryptography. Okay. All of this is possible because NVIDIA is providing the quantum platform. At the backbone of it, there is CUDA-Q, which is our open source software platform for accelerated quantum supercomputers. But underneath it, we have extremely good accelerated quantum simulation frameworks based on GPUs like cuQuantum and DGX Quantum, our reference architecture for low latency integration with quantum computers. So this is happening today, okay? On top of all of this, we have CUDA-QX. This is where I'm working. And basically, this is a set of really interesting libraries that integrate the quantum platform into day-to-day research. Okay. So, well, CUDA-QX is a set of libraries, but also primitives for quantum error correction, optimized and accelerated solvers, and also software and infrastructure that allow us to integrate directly into GPU infrastructure and CUDA-Q workflows. And this is helping us to basically bring the power of the CUDA-Q stack directly into the hands of the researchers into day-to-day quantum computing research. I will explain you now what is this about. We have CUDA-QX for quantum error correction and for solvers. So let's start from QEC. CUDA-Q QEC is a set of pre-built optimized quantum error correcting codes and decoders in CUDA-Q, a built-in stabilizer simulator based on Steam, an extension point to define custom codes and custom decoders. So you can also integrate your error correcting codes and your own decoders and try to leverage the CUDA-Q platform and the GPU infrastructure. You can also generate detector error models. So this is fundamental, basically, for performing decoding. And all of this is open source. So you can go and look it up online, and you can contribute, or if you have questions, you can come to me and to my colleagues. All right. Part of the success of CUDA-Q QEC is decoding. As I said, decoding basically is a clever way to reconstruct errors that happened during the computation. And decoding is a very relevant but also very difficult task because it needs to happen in real time. And relevant quantum computing happens in this order. I would say that probably this line is a quantum error correcting code with distance 11, for example. And yeah, decoding time needs to be under the order of magnitude of a gate execution. Probably for a normal algorithm execution, this can be a little bit more relaxed, but for other routines, this is quite stringent, okay? And well, industry standards that, for example, rely on CPU algorithms are struggling because, well, as we scale the code distance, the decoding time increases dramatically. But what we can do is that we can use parallelization, for example, GPU approaches, and parallelization already helps us by employing conventional computing techniques to stay in this block, in this region, but also we can use AI, for example, and we have a linear scaling. Yeah, the first approach is parallelization by using GPUs, and we provided an implementation of belief propagation with order statistics in QEC 0.2. We had an acceleration over the CPU counterpart by 35x, even in a noisy environment. And also, there is the possibility of performing batch decoding, and this is really relevant because in a normal algorithm, during fault-tolerant quantum computation, what is relevant actually is throughput. And once you have 10,000 syndromes, for example, it is possible to even more accelerate by 42x your decoding on the CUDA-QX platform. All right, these benchmarks are derived on the bicycle code, 144.12.12, for those who are familiar with it. This is basically state of the art. And I would like to invite you to check out this decoder because this is probably one of the best decoders out there right now. Okay, And I want to show you also an example of AI for decoding, because this is the AI and Quantum Summit. Well, basically, we have an example of a decoder for a very interesting task, and very difficult one, actually, which is magic state distillation and production. Magic states are the secret ingredient to quantum computing. Without magic states, without magic, now this is a kind of a buzzword, but yeah, magic is basically non-Cliffordness. For the technical people. And well, this is very difficult because it requires lots of resources, and it's difficult also to, once you produce a T-state, that is actually of a high quality. And without, this has to be a fault-tolerant procedure, and requires decoding. And we, in partnership with QERA, we were able to create a transformer-based AI decoder based on a error-correcting code with distance 3. And this allowed us to increase the acceptance ratio of the T-state and the quality of the fidelity of the T-state that we produced. And this is a pretty big breakthrough. The transformer-based decoder has been benchmarked against the most likely error decoder. And yeah, we can see that we go from 45 milliseconds to 1 millisecond. This is already pretty good. And yeah, another interesting result is that we can deploy this in real time. And also, we were able to train the AI decoder with simulation data based on an error model of the QERA machine, instead of actually retrieving error and noisy data from the quantum machine directly. OK, I want to show you also something about the CUDA-QX solvers. And this is also very interesting. I really like it. The CUDA-QX solvers are a set of accelerated variational quantum algorithms, but what is more important is the fundamentals of it. We have quantum chemistry tools, operator infrastructure for defining your own algorithms and your own models. We have optimization algorithms that are even more accelerated, and more is coming soon. And all of it is open source again, so you can check it out. Well, I want to show you a very interesting example. There is a challenge. Variational quantum algorithms offer the promise to well, run drug discovery applications, but suffer from serious optimization issues. This is the typical barren plateaus and trainability issues of variational quantum algorithms, because, well, the landscape of the parameters of these algorithms is difficult. So yeah, a solution is to generate quantum circuits with a GPT. In the same way that we generate sentences word by word, we want to generate quantum circuits gate by gate. And once we provide the GPT a pool of operators, and that is compatible with the device, with the Hamiltonian of the problem that we want to solve, then we can generate a quantum circuit. This is a collaboration with the St. Jude Children's Research Hospital and the University of Toronto. This is pretty interesting because it's a new approach. And this approach, well, has a speed of 40x over CPU implementations. But OK, I want to delve a little bit more into the details of why is this relevant. Because, yeah, it's just a GPT, but no. The goal is to find a circuit that is able, for example, to produce a ground state and optimization of some possible space of a circuit. And usually what variational quantum algorithm does, the VQE, is optimizing the parameters of the ansatz of a fixed structure, okay, with the pros and cons, the overheads of a fixed structure, by iterating over this optimization process that is based on the estimation of by estimating the energy, the ground state energy at the end of the CPU, QPU. But what we are doing here is that we are trying to avoid the optimization over the circuit, over the parameters, and we move our cost function from a quantum landscape, and we take it identically, and we move it to a classical landscape. The landscape is identical, but we're improving our trainability, okay? Because we are avoiding the barren plateaus of a quantum computer by using backpropagation on the classical neural network. And, well, we are able to improve trainability, because backpropagation has better strides than VQE. And we don't have, for example, to use an ansatz, a fixed ansatz that can be very limiting. But by sampling different circuits, we are able to explore a much better solution space. And well, this was used for estimating the ground state of molecules quite successfully. And this was performed on A100 GPUs on the Perlmutter supercomputer. But this can be extended to different properties. This is not the only application. And what we can do is also use transfer learning. So this is very relevant, because once you have trained your LLM, what you can do is that you can change the environment, change slightly the geometry, and this is still going to work. And what else you can do is that you can change also the molecule. Once you train for a set of molecules, what you can do is that you can take this knowledge and reuse it for different molecules once again. And, well, I mean, this method works also for different domains. As I said, the secret ingredient is the pool of operators that you use, your gate set. But what you can do is that you can switch the gate set, you can switch operator pool, and the GPT is going to work in the same way with the same benefits. Thank you very much for your attention. I hope that you are happy with this presentation, that I gave you a nice round tour of the NVIDIA landscape. You can check out CUDA-Q by doing pip install. It's open source. You can check out also the libraries. If you have questions, reach out to me outside, online, and we are always happy to work with the community. Okay? Thank you very much.